What connects the blood flowing through your veins? The very first sparks of life on Earth, a legendary Viking sword, and the crimson dust covering the surface of Mars.
That is quite the list.
Right. Think about it for a second. It sounds like the setup to some kind of weird riddle. But the answer is actually just a single, incredibly abundant element.
Iron.
Exactly. Iron.
And, it really is the defining element of our planet's history. Like, when you look at the entire geological and biological timeline, iron isn't just a participant, it's the actual infrastructure.
Yeah, and that is the perfect setup for what we are doing today in this deep dive. We are tracing the ultimate biography of iron.
It's a huge topic.
It is. Our goal is to figure out how this one specific metal managed to act as the master catalyst for, well, biology, geology, and human civilization. Okay, let's unpack this. We have a massive stack of research in front of us today.
We really do.
We're looking at origins of life chemistry from the Max Planck Institute, some wild geological research from Caltech on ancient ice ages, data from Planetary radio about Martian dust, and even modern metallurgical economics.
It's a lot of ground to cover.
It is. And I want to start by looking at iron, not as, just a metal we build bridges out of, but as the literal engine of planetary evolution. Because honestly, iron is like the ultimate character actor of the universe.
A character actor. I like that.
Yeah. It's always in the background, holding the scene together, but actually it's driving the entire plot.
If we connect this to the bigger picture, to understand that engine, you have to kind of strip away the modern context of steel. You have to look purely at the atomic behavior.
Right, getting down to the chemistry.
Exactly. Iron's true power lies in its chemical flexibility, its ability to bond, to rust, to mediate the transfer of electrons in these incredibly hostile environments. Long before it was structural, long before we were making beams out of it, it was functional.
Functional. Okay, and to see that function, we have to rewind the clock. Like all the way back to the very beginning.
Back to early Earth.
Right. We're looking at early Earth. And it is a hostile, barren rock. The atmosphere is completely devoid of oxygen. It's heavy with carbon dioxide and water vapor, and it's under massive pressure.
Not exactly a vacation spot?
No, not at all. But somehow, in that exact environment, the molecular building blocks of life emerge. And the research we have here from the Max Planck Institute points to something called the Fischer-Tropsch process.
Which is fascinating.
It's wild because, I looked this up, and that is an industrial chemistry technique. It's used to synthesize liquid hydrocarbons today.
It is. In a modern setting, the Fischer-Tropsch process requires these highly controlled reactor vessels. You need specific high temperatures, and you need refined metallic catalysts to convert carbon monoxide and hydrogen into complex organic molecules.
Right, like multi-million-dollar chemical plants.
Exactly. But the researchers at Max Planck, along with the Ludwig Maximilian University of Munich, they demonstrated that early Earth was essentially running a planetary-scale, super messy version of this exact industrial process.
Driven by meteorites and volcanoes.
Yes.
Wait, I need to push back on this immediately. Because the Fischer-Tropsch process in a lab requires incredibly precise pressure and temperature controls to yield anything useful. So how does, a random atmospheric soup of carbon dioxide and space dust replicate a highly controlled chemical plant?
Well, it comes down to surface area, specifically the immense surface area provided by the dust itself.
Okay, break that down for me.
We are talking about meteoritic ablation.
Ablation meaning burning up.
Right. When an iron-rich meteorite, like the Campo del Cielo, for example, falls through that thick early Earth atmosphere, the friction doesn't just break it apart, it literally vaporizes the iron.
It just turns it straight into a gas.
Exactly. And as that vapor cools in the upper atmosphere, it condenses into these tiny, nanometer-sized iron particles.
Just a fine mist of iron.
Yeah. And we're also seeing similar nanoparticle production from the ash of highly active, hyperviolent volcanoes. Think of the modern plumbing of Mount Etna, but on a vastly larger scale. So you end up with an atmosphere completely saturated with iron nanoparticles.
So because there's so much of it and the particles are so small, the scale and the particulate size essentially compensate for the lack of a controlled reactor.
Exactly. Because these particles are nanometer-sized, Their surface area to volume ratio is just astronomical.
Right, tons of surface area for reactions to happen on.
Right. So when they settle into these high pressure, high temperature, CO2 rich environments like deep hydrothermal vents or the slopes of these volcanoes, they provide billions of microscopic reaction surfaces.
And that's where the chemistry happens.
Yes. The CO2 and hydrogen molecules adsorb, meaning they stick to the surface, not absorb into it, but stick to the outside of these iron nanoparticles.
Okay, got it. Adsorb with a D.
Exactly. The iron essentially acts as a wedge. It facilitates the breaking of the strong carbon-oxygen bonds and helps form new carbon-hydrogen bonds. And the crucial thing here is that because iron is acting as a catalyst, it isn't consumed in the reaction.
Oh, right. So the new molecule forms, drifts away, and the iron particle is just sitting there immediately ready to do it again.
Endlessly reusable. It's just a tool on the assembly line.
And the output of this natural reactor isn't just random sludge either. The Max Planck sources mention that in the pressurized chamber experiments, the ones simulating these exact early Earth conditions, the iron nanoparticles successfully produced methanol, ethanol, acetaldehyde, and formaldehyde.
Which is a huge deal.
Yeah.
Because while those aren't biological molecules themselves, they are the non-negotiable precursors.
Right, you can't have life without them.
Exactly. Acetaldehyde and formaldehyde are the foundational chemical steps required to synthesize fatty acids, sugars, amino acids, and the nucleobases that eventually form DNA and RNA.
It's mind-blowing. So the raw materials raining down from space provided the infinitely reusable factory equipment to manufacture the chemical Legos of life.
That's a great way to put it.
But having the building blocks is really only half the equation, right? Because once those building blocks assemble into something resembling basic life, that life needs energy to survive.
It needs a metabolism.
Right. And there's no photosynthesis yet. There's zero oxygen.
This is where we look at the vector-Schweitzer theory, specifically the iron-sulfur world theory.
Oh, yeah. The Ginter-Vector-Schweitzer paper.
Right. He proposed that early life didn't just happen to exist around iron. It was metabolically dependent on the thermodynamic energy released by iron-sulfur transformations.
So the iron was the power source.
Yeah.
And the core mechanism here, looking at the microbiology paper we have, is the chemical reaction between iron-2 monosulfide, that's FeS, and hydrogen sulfide, H2S.
Correct.
And when those two interact down in the deep, dark ocean sediments, they form pyrite, FeS2, and they release hydrogen gas.
And pyrite is, of course, what we commonly call fool's gold.
Right.
But in the deep biosphere, it's not just a shiny rock. It is the primary byproduct of an essential energy exchange. The research from the Proceedings of the National Academy of Sciences takes this purely geological theory and proves that it's a biological reality.
Right, the PNAS paper. They isolated a specific microbial enrichment culture from deep sediments. They called it culture J5.
Yes. And they found that at a very specific ambient temperature of 28 degrees Celsius, the transformation of FeS into pyrite isn't just a slow rock-forming process. It is being actively mediated by the microbes themselves.
Which is crazy. And the timeline of this experiment is what really caught my eye. The researchers didn't just, mix some chemicals in a beaker and watch it fizz for an hour.
No, this was a long-term observation.
Yeah, they monitored these cultures over periods of 3 to 8 months, and they used Nussbauer spectroscopy to watch the atoms literally rearrange themselves.
Nussbauer spectroscopy is absolutely critical here because it doesn't just tell you what elements are present in the sample. It tells you the oxidation state and the local environment of the iron nuclei.
Okay, how does that work? Simply.
It relies on the recoil-free emission and absorption of gamma rays. Basically, on the data readout, you look for specific doublet peaks.
Like twin spikes on a graph.
Exactly. Twin spikes that correspond to how the iron atoms are vibrating and bonding in the crystal lattice. And over the course of 7 months, the researchers watched the initial doublet peaks of the FeS mineral phase slowly vanish.
Just fade away.
And they were replaced entirely by the distinct signature doublets of pyrite.
Wow. But the microbes aren't just sitting there cheering the iron on.
Right.
The PNAS paper states that this pyrite formation is centrifugally coupled to methanogenesis. And I really want to break down the mechanics of that because the centrifuge is doing a lot of heavy lifting in that sentence.
Centrifuge in microbiology is essentially a thermodynamic partnership. It occurs when a chemical reaction won't proceed on its own because the accumulation of the byproduct stops the reaction.
Like a traffic jam?
Sort of. It's a basic principle of chemical equilibrium. In the case of FeS and H2S reacting to form pyrite, the byproduct is hydrogen gas.
Right.
If that hydrogen builds up in the immediate microscopic environment, the reaction physically cannot continue. The pressure of the product pushes back against the reaction.
So the chemistry essentially chokes on its own exhaust.
That is exactly what happens. And this is where the specific archaeon identified in culture J5 comes into play. It's called Methanospirillum stamzi.
Methanospirillum stamzi.
And it survives via hydrogenotrophic methanogenesis, meaning it uses hydrogen gas to reduce carbon dioxide and create methane.
It's eating the exhaust.
Yes. It is constantly, aggressively scavenging the hydrogen the exact millisecond it is produced by the iron-sulfur reaction. By continuously removing the hydrogen, the archaeon keeps the local hydrogen pressure near zero.
Which clears the traffic jam.
Exactly. It creates a thermodynamic vacuum, which chemically pulls the festopyrite reaction forward.
That is incredible. And the researchers proved this obligate dependency by throwing a literal wrench into the system, didn't they?
They did. They introduced a specific methanogenesis inhibitor, a chemical called 2-bromobathan sulfonate.
And that just stops the archaeon from consuming the hydrogen.
Right. And the moment the microbe was paralyzed and stopped eating hydrogen, the geological formation of pyrite completely flatlined.
Because the exhaust built up again.
Exactly. The biology and the geology are locked in a codependent loop. This sustains what microbiologists call the cryptic sulfur cycle in the deep biosphere.
Cryptic because it's hidden.
Because it operates in total darkness, requiring absolutely no sunlight, entirely fueled by the electron transfers of iron and sulfur deep underground.
Okay, so if you were listening to this, I want you to imagine early Earth, not as a warm, lightning-struck soup of chemicals, which is the classic image, right? But as a planet-sized, iron-fueled battery. Deep at the hydrothermal vents, iron is constantly rusting into pyrite, bleeding off a steady stream of hydrogen and literally powering the first microbial ecosystems into existence. Iron was the power grid.
It was the power grid. But, the fascinating thing about planetary systems is that the elements that generate energy can also sequester it. The same iron that provided a microscopic power grid eventually played a central role in a macroscopic climate catastrophe.
Oh, man. Yeah, we are jumping ahead in the timeline now. We're looking at the late Proterozoic era, roughly 800 million years ago. And the geological research we have from Caltech details an event known as Snowball Earth.
Which is exactly what it sounds like.
Yeah, we're talking about a global glaciation so severe that ice sheets reached all the way to the equator. Like, the entire planet was a giant snowball.
And the evidence for this is largely paleomagnetic. Geologists look at ancient rock formations, like the Alatina Formation in South Australia.
And what are they looking for in the rocks?
Well, when sedimentary rocks form, any magnetic minerals within them align with the Earth's magnetic field at that specific latitude, almost like millions of tiny compass needles freezing in place.
Oh, that makes sense.
So by analyzing the magnetic inclination trapped in these ancient rocks, alongside the presence of massive drop stones.
Drop stones?
Yeah, boulders carried out to sea by glaciers and then dropped into fine marine sediments as the ice melts. By finding those drop stones mixed with rocks showing an equatorial magnetic signature, we know definitively that massive glaciers were sitting at sea level in the tropics.
Which is wild to think about. Glaciers in the tropics.
Yeah.
But the physical mechanics of how the entire planet freezes over, according to the Caltech paper, start with the arrangement of the continents. They outline the trigger. It was a massive concentration of land masses right in the low-latitude tropics.
Right, because if you have extensive continents clustered around the equator and you have a slight drop in global sea levels, perhaps from early tectonic shifts, you suddenly expose vast areas of shallow epicontinental seafloors.
Just a lot of bare dirt and rock facing the sun.
Exactly. And land, especially bare rock, has a much higher albedo than deep ocean water.
Albedo meaning reflectivity.
Yes, it reflects solar radiation back into space rather than absorbing the heat like the dark ocean does.
So the Earth literally starts rejecting the sun's heat. The temperature drops globally, and the polar ice caps start to grow.
And this initiates a runaway albedo feedback loop, because ice is even more reflective than bare land.
Right. It's bright white.
So as the ice advances toward the equator, it reflects more heat, which makes the planet colder, which creates more ice. It's a vicious cycle. And once the ice crosses a critical latitude threshold around 30 degrees, the feedback becomes unstoppable. The oceans quickly freeze over completely.
A global ice lid.
A global ice lid.
And that lid shuts down the two most critical regulatory systems on the planet. First, it physically decouples the ocean from the atmosphere, meaning there is zero oxygen exchange. The ocean becomes completely anoxic.
It suffocates.
Right. Second, because the continents are buried under miles of ice, the hydrological cycle just freezes. Rain stops falling on rock, which means silicate weathering, the primary geological mechanism that pulls CO2 out of the atmosphere, grinds to a complete halt. And the biological pump stops because photosynthesis under the ice just collapses.
So you now have a stagnant, pitch black, suffocating global ocean. But, and this is where the iron comes back in, the mid-ocean ridges at the bottom of the sea are still highly active.
Because the tectonic plates are still moving.
Right. They're constantly pumping out hydrothermal fluids rich in ferrous iron, F2 plus sound.
And Ft plus is the soluble form of iron, right? It dissolves in water. And because there's absolutely no oxygen in the water to react with it, the iron doesn't rust. It just stays dissolved.
Exactly. Over the course of millions of years of this deep freeze, the entire global ocean becomes a saturated chemical pressure cooker of dissolved ferrous iron. It's a loaded spring, just waiting for the reintroduction of oxygen.
And the release of that spring comes from the volcanoes. Because even though the Earth is covered in ice, volcanic activity hasn't stopped. Volcanoes are punching through the ice sheets, continually erupting and pumping carbon dioxide into the atmosphere.
But remember, because the silicate weathering process is broken by the ice, the atmosphere has no way to scrub the CO2 out.
Right, it just piles up.
The carbon dioxide simply accumulates. It builds up to staggering levels, potentially hundreds of times higher than modern atmospheric concentrations. And it keeps building until the greenhouse effect finally overpowers the extreme albedo of the ice.
And the thaw begins. And when it goes violently. The ice melts, the global wind patterns re-engage with the water, and massive violent ocean circulation restarts. The deep iron-saturated waters are violently upwelled to the surface,
where they crash into an atmosphere heavily laden with oxygen.
Here's where it gets really interesting. Because the thermodynamics of the reaction dictate that it happens almost instantaneously on the geological timescale. The soluble ferrous iron, the F2 plus Paris, reacts with the newly available oxygen and is stripped of an electron. It becomes ferric iron, F3 plus Paris.
And ferric iron is highly insoluble in neutral pH water.
So if you picture shaking up a frozen snow globe, right? Once it thaws, all the iron rusts and falls to the bottom at once. The entire ocean rusts at once.
The iron precipitates out of the water column and falls to the seafloor as a massive blanket of oxidized metal. This global event created the cap formations of the banded iron formations, specifically deposits like those found in the Rapitan Group in northern Canada.
You can actually see this today.
You can. You can look at the rock record in Canada and see massive layers of pure iron oxides interbedded with glacial tillites and those drop stones we mentioned earlier. It is a literal snapshot of the ocean clearing its throat at the end of Snowball Earth.
It's an apocalyptic visual, a rusted ocean falling like red snow. But the evolutionary biology sources we're looking at point out that this wasn't just a massive chemical reaction, it was a planetary reset button.
It was a brutal evolutionary bottleneck. The deep freeze and the subsequent toxic rusting event cleared out the old, stagnant, dominant biota of the Proterozoic oceans.
Just wiped the slate clean.
But by pulling all that dissolved iron out of the water column, it fundamentally altered the ocean's chemistry. It made it far more hospitable for complex life once the dust settled.
Which sets the stage for the Ediacaran fauna.
Exactly. The first clear, fossilized record of complex, macroscopic, multicellular metazoan animals, the lineage that eventually leads to all complex animal life, including us, exploded into the ecological vacuums left behind by Snowball Earth.
The irony is just wild. The exact same mechanism that nearly sterilized the entire planet paved the way for our existence.
It's a profound thought.
It is. But let's dig into the chemistry of that rust falling to the seafloor. We've talked about the macroscopic scale, the global oceans, but the microscopic structure of rust is actually the key to understanding not just our past, but the history of our closest planetary neighbor. We're looking at Mars now.
Right. And to understand the Martian surface, we have to establish the baseline of how iron rusts on Earth under normal oxidizing conditions. When iron-bearing minerals weather on Earth's surface today, they primarily form a mineral called hematite.
And we've got the data from the Virtual Museum of Minerals here on this. Hematite's chemical formula is Fe2O3. It's a very common iron oxide. I mentioned this earlier, but it's named from the Greek word hematites, meaning blood-like.
Because if you scratch it across an unglazed porcelain streak plate, it leaves a vivid blood-red line.
Right. Even though the rock itself might look gray or black, the powder is red.
Yes, and the physical properties of hematite are defined by its corundum-like crystal structure. If you zoom into the atomic level, hematite consists of a dense, closed hexagonal packing of oxygen atoms. The ferric iron ions, the Fe3, they sit inside the microscopic gaps between the oxygen atoms. Specifically, they occupy two-thirds of the octahedral sites in the lattice.
An octahedral site, meaning the iron atom, is surrounded by 6 oxygen atoms, shaped kind of like an 8-sided die.
Correct. And because ferric iron has a +3 charge and oxygen has a -2 charge, the 2:3 ratio of Fe2O3 means the structure is perfectly electrically neutral, there are no loose bonds, it is dense, it is physically hard, and it is chemically inert in most surface environments. But most importantly, it is completely anhydrous.
Anhydrous, meaning it contains 0 water molecules within its mineral structure. It's totally dry.
Totally dry. And for a very long time, the consensus among planetary geologists was that Mars was red because it was dusted in this exact anhydrous hematite.
Which, it made logical sense. We knew Mars had lost its surface water billions of years ago.
Yeah.
So the assumption was that the iron-rich basalts on the surface had slowly, painstakingly oxidized over eons of exposure to the thin, dry atmosphere and the harsh solar radiation, eventually stabilizing as hematite.
And this seemed to be confirmed when the Opportunity rover discovered those famous blueberries, those small spherical concretions of hematite scattered across the Meridiani planum.
Yeah, those pictures were everywhere. But the new research completely upends the dry rust theory. We're looking at the Planetary radio interview with Adonis Valentinus, and his team's findings are a total paradigm shift. And honestly, the methodology of how they figured this out is a masterclass in experimental physics. Because, we don't have a jar of Martian dust sitting in a lab on Earth to test.
We don't. We only have remote orbital spectroscopy. Satellites basically bounce light off the Martian surface and measure which wavelengths are absorbed and which are reflected back. But to accurately interpret that light signature, you need a physical analog on Earth that matches not just the chemical composition, but the exact physical grain size of the dust.
Which is incredibly difficult because Martian dust isn't like beach sand. It's unbelievably fine.
All right.
Valentinus and his team took terrestrial basalts and iron oxides, and they had to physically grind them down in the lab until the particles were roughly 60 times smaller than a single human hair.
They had to achieve a nanoscale particulate size to match the aerodynamic suspension and settling patterns of the dust on Mars. Because if the grain size in the lab is off by even a fraction of a micrometer, the way light scatters through the crystal lattice changes, and the spectral signature won't match the orbital data, it'll throw the whole reading off.
Right, it's that sensitive. So they finally get the terrestrial dust ground down to this absurdly fine powder. They run the spectroscopy, and they compare it to the Mars orbiters. And the signature doesn't match pure hematite.
No, it doesn't.
It's heavily dominated by a different iron oxide altogether, called ferrihydrite. Okay, let me push back a bit from a lay perspective. If ferrihydrite and hematite are both just different molecular arrangements of red iron oxide, does it really matter which flavor of rust is blowing around out there?
This raises an important question. Because yes, it absolutely matters. It fundamentally rewrites the hydrological timeline of the entire planet.
Because of the water.
Yes. Hematite, as we established, is anhydrous. Ferrihydrite is hydrated. Its molecular structure physically traps water molecules and hydroxyl groups within the lattice itself.
So the water is chemically locked in the rock.
Furthermore, on Earth, ferrihydrite does not form via dry atmospheric weathering. It is a precipitate that only forms in the direct presence of liquid water, often in cold, iron-rich aquifers, glacial runoff streams, or deep marine sediments.
So the dust on Mars didn't form after the oceans dried up.
No. If the dominant dust on Mars is ferrihydrite, it means the entire surface of the planet rusted while it was still wet and freezing cold. The red dust isn't the ash of a dead planet. It is the direct chemical relic of a wet, dynamic, and potentially habitable era.
Wow.
The water didn't just evaporate into space. A massive portion of it was chemically locked inside the rust itself.
Which presents an incredible logistical advantage for human exploration. I mean, if you are an astronaut trying to survive on Mars, your biggest bottleneck is water. You can't carry enough of it from Earth. It's too heavy.
It's too heavy.
But if the dust covering the entire planet is hydrated ferrihydrite, you don't need to drill deep ice cores at the poles. You can literally scoop up the surface dirt, seal it in a low-pressure oven, apply heat, and the ferrihydrite lattice will break down. It will outgas the trapped water vapor, which you can then condense and drink.
The rusted surface that signifies the death of the Martian oceans might be the exact mechanism that keeps future human colonies alive.
That is just incredible. But, the technology to build those habitats, to construct the pressurized rovers and the extraction of, as we just talked about, is entirely dependent on humanity's mastery of extracting iron here on Earth.
It is.
And the history of how we figured that out involves a massive 2,000-year technological delay. Let's look at the transition from the Bronze Age to the Iron Age.
Let's do it. But it's important to clarify up front that humans were interacting with iron long before they knew how to mine it. We have the meteoric prelude.
Right. The space rocks. Because before we could dig iron out of the Earth's crust, it literally fell from the sky.
Exactly. Meteoric iron is unique because it arrives as a natural iron-nickel alloy. It is already in a stable metallic state. It doesn't require smelting to remove oxygen.
It's just a chunk of metal sitting in the desert.
Right. So ancient peoples could simply find these heavy, metallic rocks and cold hammer them into shape. The historical records point to artifacts like the iron beads found at Giza in Lower Egypt, dating back to 3200 BC, or the famous dagger found in the tomb of King Tutankhamun, which was forged entirely from a meteorite.
They were essentially cosmic scavengers.
Basically, yes.
But the core question posed by the Mansi 81 historical metallurgy source is fascinating. The Bronze Age was in full swing by 3500 BC. Humanity was building entire empires with bronze. But the Iron Age didn't officially begin until around 1200 BC. Why did it take over 2 millennia for human civilization to figure out how to dig iron out of a mountain when we already had a highly sophisticated metalworking industry?
The delay wasn't a lack of curiosity, it was a literal wall of thermodynamics. To understand the jump to iron, you have to understand why bronze was so achievable in the first place.
Okay.
Bronze is an alloy, primarily of copper and tin. Copper melts at 1085 degrees Celsius. Tin melts at a remarkably low 232 degrees Celsius.
And those temperatures are easily reachable in a standard Neolithic pottery kiln.
Right.
You stack the wood, you force some air in with bellows, the ore melts, the metals mix into a liquid pool. You just pour it into a clay mold.
It's basically liquid casting.
Right. You crack the mold, and you have a perfectly shaped, incredibly durable axe head or a sword.
But iron ore, on the other hand, is mostly hematite or magnetite, meaning the iron is locked in a tight molecular bond with oxygen. To break that bond and separate the metal, you have to initiate a smelting process that requires a staggering temperature of at least 1250 degrees Celsius.
Which is way hotter.
A wood fire in a standard kiln will never reach that temperature, ever.
So how did they finally crack the physics of it? How did they get it hot enough?
They had to invent the bloomery furnace. A bloomery is essentially a clay chimney designed to create a highly specific internal atmosphere. You pack it with alternating layers of crushed iron ore and charcoal.
Alternating layers.
Yes. And the charcoal is crucial because it serves a dual purpose. First, when you blast it with constant forced air from bellows, it burns hot enough to finally hit that 12,250 degree threshold.
But it doesn't melt the iron, right?
Yeah.
Because pure iron doesn't melt until over 1,500 degrees Celsius.
Exactly. The iron remains solid the entire time. This is where the second function of the charcoal comes in. As the charcoal burns in a slightly oxygen-starved environment inside the chimney, it produces carbon monoxide gas.
Right.
The carbon monoxide acts as a reducing agent. As the gas rises through the hot iron ore, it physically rips the oxygen atoms away from the iron oxide molecules, creating carbon dioxide, which exhausts out the top.
That's the B.O.O.G reaction. The gas is chemically stripping the rust in real time.
Precisely. And what's left at the bottom of the furnace is not a neat pool of liquid metal that you can pour into a mold.
Right, because it never melted.
It is a bloom. A spongy, porous, glowing mass of solid iron intermixed with pockets of liquid, glassy slag made of melted silica and impurities.
And the processing of that bloom is where the real nightmare begins. Because you can't cast it, the smith has to pull this glowing sponge out of the furnace with tongs and immediately start pounding it with heavy hammers. It's almost like kneading bread if the dough is 1,200 degrees and full of liquid glass.
It's incredibly violent work.
You have to hammer it, fold it over, and hammer it again, physically squeezing the molten slag out of the pores to consolidate the iron into a solid, dense bar.
And through that repetitive heating in the charcoal forge and relentless hammering, trace amounts of carbon slowly diffuse into the outer layers of the iron. This accidentally creates very early, very primitive steel. It was an intensely complex, exhausting, labor-intensive process.
Which brings us to the obvious economic question. If bronze is so much easier to make and you can mass produce it by just pouring it into molds, why would ancient societies ever abandon it for the grueling labor of bloomery iron.
They didn't want to abandon bronze. They really didn't. They were forced to by the collapse of global supply chains.
The Bronze Age collapse.
Right. Around 1200 BC, the ancient Near East experienced the Late Bronze Age collapse, a cascading series of systemic failures, famine, war, mass migrations, completely shattered the intricate trade networks that sustained the Bronze Age empires.
Because bronze requires tin, and tin is geologically rare. You can't just find it anywhere. Kings relied on massive, continent-spanning trade routes to bring tin to their copper mines. When the trade routes died, the bronze industry evaporated overnight. No tin means no bronze.
Exactly. They had to figure out iron out of sheer desperation.
And the irony of early iron weaponry is that, metallurgically speaking, it was inferior to good bronze.
It was. Early bloomery iron, before they mastered consistent steeling, was softer. It wouldn't hold a razor edge as well, and it rusted constantly.
Right, it's a total myth that iron swords simply chopped through bronze swords and conquered the world. A nobleman's bronze sword was a vastly superior piece of metallurgy. But iron possessed one overwhelming strategic advantage: abundance.
It's everywhere.
Iron is the fourth most abundant element in the Earth's crust. It is quite literally under your feet almost everywhere on the planet. I compare it to fast food. It wasn't Michelin star quality like a noble's bronze sword, but iron ore was so abundant you could suddenly equip an army of thousands instead of just the elite guard.
That's a great analogy. The geopolitical shift wasn't about the quality of the metal, it was entirely about the scale of production. In the Bronze Age, an empire might have enough metal to equip an elite chariot guard of a few hundred men. But once a society cracked the thermodynamics of the bloomery furnace, they no longer needed to trade for rare tin. They could mine the local hills and suddenly afford to equip an army of tens of thousands of conscripts with iron spears.
Abundance overthrew the elite. It democratized warfare and agriculture, because now you have iron plows too. And once the technique was proven, it spread like wildfire.
The archaeological record tracks the explosion of iron technology spreading outward from Anatolia and the Caucasus. It moved into Europe, driving the rise of the Hallstatt and later Latin cultures. It pushed eastward into Asia, fundamentally altering the agricultural capacity of the Ganges Valley.
And the Matsi 81 source makes a critical point about independent invention. Ironworking didn't just spread from one single origin point in the Middle East. In sub-Saharan Africa, cultures like the Nak in modern-day Nigeria were independently building sophisticated bloomery furnaces and smelting iron as early as 550 BC, completely disconnected from the Eurasian developments.
It was a technological inevitability. The moment human societies figured out how to unlock the massive thermodynamic potential of iron, it altered the trajectory of human civilization on literally every continent.
And the legacy of that shift, the realization that the true power of iron is its sheer unyielding abundance, is exactly what dictates the structure of our modern world today. We've moved from the ancient bloomery forge to the staggering mechanized scale of modern economics.
Absolutely. When we talk about the iron industry today, we are almost exclusively talking about steel. The data from the assay guide provides a sobering statistic. 98% of all mined iron ore goes directly into the production of steel.
98%.
It is the skeletal structure of every modern city, every shipping fleet, and every railway network on the planet.
The infrastructure required to dig that much rock out of the ground and turn it into skyscrapers is almost beyond comprehension. I mean, it starts with open-pit surface mining. Giant autonomous excavators, some the size of apartment buildings, tear into the earth, extracting the raw hematite and magnetite ores. But you can't just throw raw boulders into a blast furnace, can you?
No, you can't. The ore has to be beneficiated. It is transported to massive processing plants where crushing circuits physically grind the solid rock down until the individual pieces are no larger than a marble.
But even then, the iron is still intimately mixed with gangue.
Yes.
Yeah.
Gangue is the commercially worthless rock.
The silica, the alumina, the phosphorus that surrounds the iron minerals. Because if you leave the gangue in the mix, it will catastrophically weaken the structural integrity of the final steel product.
The processing plants use magnetic separation and flotation tanks to strip the gangue away, leaving behind pure iron or fines, basically a highly concentrated iron dust.
Right.
But here is the industrial bottleneck. You cannot feed dust into a modern blast furnace.
Why not?
Because a blast furnace operates by blowing massive volumes of superheated air up through the bottom of the stack to drive the reduction reaction. If you dump fine dust into the top, the massive updraft will literally blow the raw materials straight out the exhaust
It's like
stacks.
the giant red cloud over the factory.
Exactly, so they have to agglomerate it. They use a process called sintering, and the mechanics of sintering are fascinating. They mix the iron fines with a small amount of coke, which is pure carbon and flux, and they run it on a continuous conveyor belt under a massive ignition hood.
Okay, so they're baking it.
Right. The heat essentially semi-melts the outer edges of the iron particles, fusing them together without entirely liquefying the metal. It bakes the dust into solid porous lumps or pellets.
And those are heavy enough to sink.
Yes. Heavy enough to sink through the violent updrafts of the blast furnace while remaining porous enough for the carbon monoxide gas to penetrate and strip away the oxygen.
Which is the exact same chemical boudoir reaction as the ancient bloomery furnaces, just scaled up to produce millions of tons of liquid pig iron a day.
The exact same chemistry.
And the sheer tonnage is where the modern economics get wild. Australia is the undisputed king of global iron ore. The Essay Guide notes that in 2023, Australia produced an estimated 880 million tons. The vast majority of that is ripped out of the rusty red cliffs of the Pilbara region in Western Australia.
To contextualize that dominance, the global runner-up is Brazil, driven heavily by Vale's massive Carajás mine, which produced about 410 million tons. So Australia is outproducing the second-place country by more than double.
But the volume of rock being moved is only half the story, right? The financial volatility of this market over the last 2 decades is staggering. Historically, iron ore was a boring, stable, low-margin commodity. The price hovered steadily below $30 a ton for decades. Mining conglomerates signed 10-year contracts and made their profits entirely on predictable volume.
Very boring.
But then the price graph completely breaks. It spikes to over $150 a ton.
And the mechanism behind that massive price shock wasn't a sudden scarcity of ore in the ground. It was a massive, unprecedented demand shock. It was driven entirely by the rapid, explosive industrialization and urbanization of China.
Because China essentially decided to build a new middle-class society from scratch. They were throwing up entirely new megacities, high-speed rail networks, and endless infrastructure projects, and they needed an ocean of crude steel to do it.
That single national initiative completely warped the global commodity market. Today, 62% of all of Australia's iron ore export demand comes solely from China.
That is wild.
The entire global supply chain of the world's most foundational metal is effectively tethered to the economic engine of a single nation. When China's property sector booms and the government injects stimulus into construction, the spot price of iron ore skyrockets globally. When China imposes economic cooling measures, or when their property developers face debt crises, the price of iron ore crashes globally.
So what does this all mean? It's an incredible vulnerability. But the Assay Guide also highlights a secondary pressure point that is about to fundamentally disrupt the entire industry, regardless of what China does. The global appetite for steel isn't going away, but the environmental cost of traditional blast furnace steelmaking is colliding with global climate initiatives.
It is a massive collision. The metallurgical reduction of iron ore using coal and coke is one of the largest single industrial sources of CO2 emissions on the planet. So the industry is currently facing massive pressure to pivot toward green steel.
Green steel.
Yes. This involves transitioning away from the traditional carbon-heavy blast furnaces and moving toward direct reduced iron technologies. These new methods use hydrogen gas or electricity to strip the oxygen from the ore instead of carbon monoxide.
Which requires entirely new infrastructure, massively altering the economics of production. Analysts are projecting that as the market attempts to balance this costly technological pivot with a cooling and rapid Chinese infrastructure growth, prices will likely stabilize downward. They're estimating around $75 a ton in 2024.
It is an industry caught between the unstoppable force of global development and the immovable object of environmental limits.
Yeah, it really is. Man, we have covered an unbelievable expanse of time and science today, from the microscopic origins of life to the macroscopic economics of global superpowers. Let's take a moment to pull all these threads together.
It's been a journey.
We started billions of years ago in a high-pressure, toxic atmosphere, watching nanometer-sized iron dust from meteorites act as the chemical catalyst, the endlessly reusable factory printing, the molecular precursors of life. We dove into the deep, dark biosphere, where microbial syntrophy relies on the precise atomic transfer of electrons between iron and sulfur to survive in the absence of the sun.
The cryptic sulfur cycle.
Right. Then we witnessed the nightmare of Snowball Earth, where a frozen planetary lid caused millions of years of dissolved ferrous iron to build up, only to violently oxidize and crash to the seafloor the moment the ice thawed, inadvertently clearing the evolutionary stage for complex animals.
The banded iron formations.
Yeah. We transitioned to the dusty surface of Mars, discovering through nanoscale spectroscopy that its red ferrhydrite dust is actually hydrated, holding the molecular memory and the actual physical water of a freezing wet past. We watched early human empires collapse under the scarcity of tin, forcing desperate societies to crack the brutal thermodynamics of the Bloomery furnace, democratizing warfare through the sheer geological abundance of iron.
The Iron Age.
And finally, we saw how that mastery of the B.O.O.G reaction scaled up to the 880 million-ton behemoths of the Pilbara, feeding the insatiable steel skeleton of modern civilization.
When you look at it in its totality, iron is the physical thread tying the cosmos, the geology of planets, the biological mechanics of the deep oceans, and the heights of human engineering together into a single narrative.
So I want you to remember that scale the next time you touch a cold steel railing on a staircase, or the next time you look up into the night sky and see the faint, steady red dot of Mars. You aren't just interacting with a piece of structural metal or looking at a dead rock. You are interacting with the master catalyst of the solar system.
And if we look forward, there's one final thought that brings this entire deep dive full circle.
Oh, lay it on me.
We discussed how the ferrhydrate dust on Mars is hydrated, right? And we discussed humanity's hard-won mastery of iron extraction. Well, when human civilization finally makes the monumental leap to colonize Mars, the physics of space travel dictate that we cannot bring all our steel from Earth.
It's just too heavy.
It's impossible. The pressurized habitats we construct to survive the deadly radiation, the structural supports for our biodomes, they will be forged on site. We will literally take the ancient thermodynamic techniques born in the desperate fires of Earth's Iron Age, and we will apply them to the hydrated rust of another world.
Wow.
We will use the oxidized ruins of Mars's ancient oceans to forge the steel framework of our future in space.
Taking the rest of a dead world to build a new one. I cannot think of a better place to leave it. Thank you so much for joining us on this deep dive. It has been an absolute masterclass.
It is my pleasure.
And thank you for coming along on the journey. Until next time, keep looking deeper.